everyone, I wanted to give you a video about a topic that we have not yet seen. I will be teaching that this week. However, I wanted you to get a heads up on it. So this graph is of what we call a slope field. It is literally the graph of the differential equation, or the derivative, dy dx equals negative x over y. And it represents all possible slopes of a graph whose derivative, or of a function whose derivative is negative x over y. For example, if we were to pick the point 1, 1, right there. If I was to pick the point 1, 1, so x equals 1, y equals 1. That means the slope of this function would be negative x over y, or a slope of negative 1. And we can see that this slope looks pretty much like a slope of negative 1. The same is true for, we'll say, this slope here, or that point there. That is negative 2, 1. That point would have a slope of negative x, so positive 2, over y, 2 over 1. And if we look, that does look approximately like a slope of positive 2. So basically steeper than a slope of 1, which happens here, and increasing. So it basically represents every single possible slope for any point on the xy plane. And the reason why it covers the entire graph is because, as you remember, when you integrate a function, you get its integral plus c. Now that plus c is what is going to determine which of these particular slopes is the correct slope for our graph, or where our slope occurs. So let's take a look at an example of an AP problem that you might see. The most recent year that had a slope field question was actually 2016. So you can tell that it's a slope field problem based on the fact that it has a graph that looks like this and a differential equation. Question A says, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated, so where all of these dots are. We need to basically draw all those little line segments indicating a possible slope. So you know that if you've got a negative slope, your little line segment's going to go down. If you've got a positive slope, your line segment's going to go up. If you've got a slope that's less than 1, then you know it's going to be kind of flat. If it's more than 1, it's going to be kind of steep. And that's about as much as they're looking for. They're not really looking for you to be exactly a slope of 2 over 1 or exactly a slope of negative 1 over 2. They just want to make sure that you don't draw a flat line as having a slope of 10 or anything like that. So if you're wondering how we would answer this question, we would just find our points. So for example, we've got this point of 0, 2, and we're just going to take that x and y and substitute into our differential equation, because this is the equation of the slope. This is dy dx. So based on this particular x and y, I will be given a particular slope. So I substitute 0 for x, 2 for y, and then simplify. So I should get a slope of 4 over negative 1, or a slope of negative 4. So that's basically a steep slope that is decreasing. So it's going to look something like this. And that's really all there is to it. All right, next one. Let's do this point of 0, 1. So my x is 0, my y is 1. If my slope formula is y squared over x minus 1, then that should be 1 squared over 0 minus 1, or a slope of negative 1. So basically less steep than this slope here, but still decreasing. And you can kind of see, if I want a slope of negative 1, it should connect here, down 1 over 1. So it should be kind of a line that goes like that. And you only want that line segment just to cover that one little dot. You don't want it to go all the way across, because again, this slope of negative 1 is only for this one particular point. It's not for this point over here, or not even for this point over here. So there would be a different slope over here. Okay, next point, my favorite point, 0, 0. So that should be 0 squared over 0 minus 1, or 0. And you can hear my dog drinking water in the background. So it's a slope of 0, which means that it rises 0 and runs however much. So it's a horizontal line. Now, you don't have to be showing all of this work for the AP test. You're literally just drawing that stuff. So all of this is just scratch work. So why don't you guys pause the video and then see if you can fill in the other 3 dots when x is 2 and y is 0, 1, and 2. And then I will put it in. So pause, 1, 2, 3. Okay, now I'm going to put it. All right, so when x is 2 and y is 0, we get a slope of 0. We can say that's a horizontal line. When x is 2 and y is 1, we get a slope of 1. So it's going to be increasing kind of a 45-degree angle if you can manage it. And then 2, 2 has a slope of 4, so steeper than this line, obviously, and increasing. Now, again, they're not going to be super picky about counting your slope. They're not going to see the rise over run or anything like that. They're just going to basically look for, is it increasing or decreasing? Is it steep or not steep? Is it steeper than the ones that it should be, or is it less steep than the ones that it should be? Basically stuff like that. So it's pretty straightforward. Let's take a look at question B. So anytime I'm doing a question, I always go for the directions. Write an equation for the line tangent to the graph of y, or f of x, at x equals 2. Okay, well, I know that this is dy dx, so if I wanted to find y, then I would have to integrate this. However, I know that to write the equation of a tangent line, I need an x value, a y value, and an m value, or dy dx. And if I look in this problem, I'm going to look a little bit further to see if they give me any information. Well, they say the initial condition is that f of 2 equals 3, and I'm finding the tangent line at x equals 2. So I know it has to be at x equals 2 based on this right here. My y value is 3, and all I need to know is dy dx when x is 2 and y is 3. So I can just go to that slope formula and plug it in. And that gives me a slope of 9. So then I get my tangent line by plugging into y minus y1 equals m times x minus x1. And there we have it. There's our tangent line. So I've answered those directions, and I just keep reading to see if I'm missing anything. Oh, use your equation to approximate f of 2.1. So this is basically just saying take your tangent line and now use x equals 2.1. Like so. And you're basically just saying, oh, okay, so if I have a graph with a tangent line, then in those points that are immediately near that tangent point, my y values for my tangent line are pretty close to the y values of the curve itself. That's all this whole question is asking. So we want to find what the approximate y value is for the original function using our tangent line. So I'm just going to simplify all of this stuff. So I get 0.1 here in the parentheses, multiply it out, I get 0.9, and add 3 to both sides, and you get 3.9. So you can basically say that when x equals 2, when x equals 2.1, sorry, the y value of the actual graph is close to 3.9, maybe close to 4. Yeah, pretty cool. So we've answered all parts of the question for question number letter B. We've written the equation of the tangent line. We've used our equation to approximate f of 2.1. Now we can move on to question C. Just a heads up, this question literally involves no calculus work, just a knowledge that dy dx is the same as slope. And that was all the calculus that you had to do for that problem. Okay, question C. Find the particular solution y equals. Okay, that is important. It's saying find y equals to the given differential equation with the initial condition f of 2 equals 3. So we have our dy dx. That's what was given to us. And we want to find y equals. Okay, well, the problem with that is that this is the derivative of y, so we need to integrate it. But I've got x and y on the same side of that equal sign. So we need to do step 1, separate your variables. So I divide by y squared on both sides, multiply by dx on both sides, and then I can start thinking about integrating so that I can get just y, not dy. one thing to keep in mind here, we've talked about this today in class, if you have something with an exponent, it's the only thing, and it's in the denominator, you need to bring that up in order to integrate it. So that should be y to the negative 2 dy equals integral of 1 over x minus 1 dx. Now, we don't bring up the x minus 1 because this is one of those simple denominator problems where, okay, we just need to integrate this whole piece knowing that this is in the denominator. So there's no algebra that can be done, but we can use u substitution. So let me do this in green. So u equals, we'd set our u equal to the entire denominator. Our du would luckily just be 1. So when we substitute in here, this would be really nice. Pretty basic integral. Now that leads us to step 2, integrate both sides. And we're going to use reverse power rule for this one right here. So that gets to y to the negative 1 over negative 1 equals, and then this would just be ln of absolute value of our u plus c. Now here I'm just going to do a little bit of rewriting. If it's a negative 1 in the denominator, that's kind of like just saying, oh, it's a negative y to the negative 1, and a negative 1 exponent means it's 1 over, so that should be negative 1 over y. And then don't forget, when you integrate to ln, it should be absolute value, and this is going to be kind of important when we do our next step. But I got to substitute back for my my u, so that's x minus 1 plus c, as I'm writing all over that work right there. Now you could go one of two ways at this point. Eventually you're going to have to solve for y. You're going to have to get y by itself. So you could go ahead and do that now, or you could first solve for your c. You're going to have to do both of those steps. You can do them in either order, doesn't matter. It just depends on which order you do it and how you go back. So I'm going to substitute for my x and my y right away and get my c value. So up top, they gave us the initial condition of f of 2 equals 3, which means that I have x equals 2 and y equals 3. Substitute those in for my equation, and I get, this. So I'm going to remember that I substituted into this equation here because that's going to be important to know. So the c value that I get from this equation is the c when y is solved like this. If you were to solve for y and then get a c value, it would not be the same c value that I get here. So I basically simplify, and this step right here is where having the absolute value is important. They might give you a problem where you're integrating into an ln and then you find your c value, and you're going to have to do some maneuvering, or you might have to do some maneuvering, and you get a negative value here. Having that absolute value is important because that negative value will have to come out positive in order for everything to work out. So luckily we didn't have anything to worry about. 2 minus 1 is a positive 1, and then ln of 1 is 0, so then we get c is negative 1/3. And this is where I say, oh, this c is based on this equation right here. So negative 1 over y equals ln of x minus 1, minus 1/3, that's c. So if I were to have solved for y, the c value that I would get would be the manipulated one based on a single y value, not a negative 1 over y. At this point, anytime they ask you to solve a differential equation, you have to solve for y. So the first thing I'm going to do is get rid of that negative. And then at this point, there's a couple of things that you could do, but the easiest one that you might want to think of is I've got a 1 over y, which is the reciprocal of what I want. So I'm basically just going to flip the left side, and if I flip the left side, I have to flip the right side. So I have to think of this entire right side as over 1. So I'm just going to flip it and say, oh, it's y over 1 is equal to 1 over all of this. Ta-da! And that is the solution to the differential equation. So for part C, a couple things. Make sure that you separate those variables. Let's try to zoom out here. Separate your variables. Make sure you have the y's on the left, x's on the right. rewrite it based on your integration that you need to do, integrate both sides, and using an initial condition, find what C is, then solve for Y, or vice versa on those last two. Just make sure that you have Y equals as an answer and there's no C in there, but an actual constant term. Ta-da! That is slope fields. Not so bad, right? So I'm going to show you one more problem on here. I'm not going to do it, but I'm just going to put it up on the screen. You can pause the screen and try it on your own. So here's another slope field problem from 2015, the year before the last one. Pause the video, check it out, see if you can do it, and when you come to class, I'll see how you did.